the techniques I'm going to be use, or we are going to explore to use one of our European projects. This project is called PITAS, as you can see from the slides. The first part I will describe a little bit about our project background, then we can better understand what we are doing and what's the techniques where I'm going to present. And then I will give a brief introduction about the biometric recognition system. And then I will present some privacy enhancement approach to address two major protection requirements which have been defined by the ISO standards. These two major requirements are the irreversibility and uninhabitability. Then I will talk a little bit about the plain text equivalent problem, and we have explored a solution to prevent this problem. And then I will summarize my talk. The project background. In our project, we have 3 partners who are providing different services for their customers. The one is to provide the e-health system. The second one is for e-commerce, they can online shopping. And the third one is the e-citizens. These 3 partners are interested to use biometric systems to do authentication for their customers. So a natural idea is that they build their own database, they build their own biometric verification system, and then they build it independently and separately. So, but to maintain a biometric system, it's quite maybe the costly. And so the idea of this project is to provide a centralized biometric authentication service database as a service. So if one of them, the customers, want to access the service, the service provider will delegate the authentication to the PITAS platform. The PITAS platform will interconnect with the users by using users' biometric information to finish the authentication part. So this idea is not new, but the new thing is that store all the biometric data in one centralized database. Because the biometric data is sensitive, so it will be quite risky to store all the biometric database in one centralized database. Especially we have all of these partners, they are distributed and located in different member states in Europe. So we are before talking about the biometric enhancement, the privacy enhancement techniques, we have to know a little bit about the biometric recognition system. So here's a basic structure how we do the biometric recognition. For instance, we need to enroll a fingerprint sample. We capture a sample from a finger, and then we extract some feature from the sample, and then from another side, when we do the verification, we also do the same to capture a sample from the finger. And this sample it usually is not be exactly the same with the sample we captured during the enrollment stage. So we also extract some feature from the sample captured at the authentication stage, and then we do some calculation to calculate how similar these 2 samples, and then to decide these 2 samples are matched or not matched by setting a threshold. So if they are very similar, they have very high similarity score, they will be matched. So, but it's also another researchers explored that do verification based on the features. They also can reconstruct your original samples. As also it seems like they can get your fingerprint by the latent fingerprint you leave on the cup. So it is possible to reverse from your template to the original samples. So the first requirement for our privacy enhancement method is to guarantee irreversibility. So according with the ISO standards, irreversibility indicates that it should be infeasible to reconstruct the original biometric data from the protected template. How can we guarantee this? One solution could be fuzzy commitment scheme. The idea of fuzzy commitment scheme is that the input will be biometric data. Is the feature extracted from the original samples. Another input is a random number, can be called a secret key. The output for the fuzzy commitment scheme is helper data. Another one is a hash value, which we call the pseudo identity. So the helper data is generated by input biometric data and out from ECC code. ECC stands for the error correct code. The idea is from the communication techniques. So we generate a random number from the pseudo random number generator S. Then we put a lot of redundancy to the S, and then have the same length, the output with the input biometric data. Then we do XOR operation to have a helper data. After that, the pseudo identity will be stored in a database. So we can see pseudo identity doesn't contain any biometric information. The biometric information maybe, it's some information are involved in the helper data, but they do XOR operation with a random number. So it's from here we can understand if you want to reconstruct the original data from the helper data, it seems infeasible to reconstruct the original samples. And also we store a pseudo identity in which doesn't contain any biometric information. So this is the enrollment stage. How can we do verification? During the verification, the input is a probe sample. The same finger, maybe the same finger captured from the fingerprint captured from the same finger. And then we do the feature extraction, and then we do the XOR operation with the helper data we generate in the enrollment stage, and then use as input for the ECC decoder. Because of the redundancy added in the enrollment stage, it could be recover the original random number S if it doesn't have so much noise, if it doesn't have so much difference between probe sample and the reference sample. So then we do the same hash for this recovered S. Then we can compare the pseudo identity, which is stored in the centralized database, to have an output. These two samples are from the same person or not. Yeah, another major requirement for the privacy enhancement is unlinkability. Unlinkability is to it indicates that a different version of the protected template can be generated from the same source, but can against cross-matching. So I will use an example to explain what is the cross-match. So for if we don't use privacy enhancement approach, for instance, the customer A, he is willing to subscribe for all of these 3 services. So he will use his face to do the biometric verification. So we do feature extraction, and the enrollment is in the centralized database. And we do the same for this person, and the enrollment his feature or biometric data in the database. But there's one case: if one of these service is compromised. So maybe one of these service which is in Spain that is compromised. His biometric data is compromised. So maybe some attacker can use his biometric data retrieved from the e-health system, then can gain the access for another 2 services. So this is called a cross-match. So we can use one to access another different services. So the idea is in unlinkability, which means the feature we extracted from the person, from the same face, but it shouldn't be used for another service. So it should be unlinkable. We return to the enrollment stage in the fuzzy commitment to see how we can to guarantee this unlinkability. So it's very simple. It's because we have a random number generator S. So we just issue 3 different numbers S. We have generate random number S1, and then we will have different helper data, also different pseudo identity. For the e-commerce, we will have another random number, and for e-citizen, we will have a third different random number. So even the W1 and PI1 are compromised, they are they are impossible to get successfully authentication for the rest of the 2 services. So this is the unlinkability requirement, which also can be achieved by using fuzzy commitment. If we simplify the fuzzy commitment scheme, so we capture the biometric data from the user, we extract the features, and then we go through the fuzzy commitment, and then we will have a hash value which will be stored in the database. Security vulnerability in this scheme, which is called plain text equivalent problem. What is plain text equivalent problem? For we can understand that if we want to access a server, we use our password. We type in our password. If the worst case, we store this password in a plain text, so the server will combine the password we typed and the password stored in the database. And then if they are the same, the server will grant access to the user. So another secure way is that we do a hash for our password. So the server store the hash result from our password in the server. So, but if an attacker also he can obtain the hash value, and he sends the hash value to the server. The server doesn't know that it's a hash value from the user or from the attacker. The server also will grant the same access to the attack. So the plain text problem is, which means that we can use this value even if it's not a plain text password, or we can use this hash value to obtain the same access level as using plain text password. Now, how to solve this plain text password problem? An equivalent problem, and one solution, it could be called secure remote password protocol. Before introducing the SRP secure remote password protocol, we have to know the Diffie-Hellman key exchange, which is the basis for the SRP protocol. The goal of Diffie-Hellman key exchange protocol is to establish a secure channel by sharing secret key. We will use this example to explain how they share a secret key. So we assume this generator is 3 and a modular is 17. So which can be public. The attacker can also know these two values. But we assume there are two secrets. For the user, the secret is 15. For the server, the secret is 13. So we can calculate a public key. For the user, the public key will be 6. For the server, the public key will be 12. So the user will send this public key to the server will send his own public key to the user. So these two public keys also can be obtained by the attacker because it is public. So after that, they can calculate a session key. So you can see they calculate the same value by using the public generator and the public prime modulator. So this 10 value will be used as a secret key, a private key to secure the channel. But there's another disadvantage. This is vulnerable to the man-in-the-middle attack, which means this attacker, if he receives the public key from the user, he will store this public key and he will generate his own public key and send his own public key to the server. And the server will receive this public key from the attacker, but he think he received it from the real user. And then server will send his public key to the attacker, and the attacker will generate his own server, it seems server public key to the real user. And then the attacker will be in the middle he can gain the information from the user and also gain the information from the server, from the both sides. The reason with the Diffie-Hellman has this disadvantage is that the Diffie-Hellman doesn't have the authentication process, which has been done by the SRP protocol. The reason is that the server, the public key from the server side contain the information, contain some private, some secret information from the server, from the user, which is we can see the V value is a hash value calculated from the password. P stands for the password. So during the enrollment stage, the user needed to calculate a hash value and put in and store it in the server. And during the authentication stage, the server will use hash value to generate a random number, not like the Diffie-Hellman. The server will generate his own random number without any secret information from the user. So actually, the SRP protocol combines two techniques. One is from the DP-HOMA, which is the basic for the SRP, and also combine the pass or authentication techniques. So we need enrollment stage. The user needed to store his password information in the server in advance, and then the server side is able. Then we have a random number which contains the information from the users. Another advantage for the SRP is the first one is the guarantee the forward secrecy. What means the forward secrecy? Which means so if there's a searching key for each conversation between user and the server. If the attacker obtains this searching key for some protocols, they will use the same searching key for each conversation. But for the SRP protocol, they will use, for each time, they will use a key, a newly generated, not the same. So after the conversation, the searching key used for this conversation will be dropped. It's not useful for the next conversation, for the next authentication process. So which means this is the meaning. So if you can guarantee the forward secrecy for each conversation, if you have a new searching key. The second advantage is provide a mutual authentication to verify the users. Another capability of the SRP is the user also can verify the server, to verify if server is a genuine or not. Because the server also will calculate verify and send it to the user side, and the user can do calculation based on the previous information. But the main information they send between each other is the two random number A and B. That they are doing the similar calculation as I explained in the DP-HOMA. So yes, now I'm going to my conclusion. So we present a solution which can do biometric verification, but we don't need to store any biometric information in the centralized database. So which means user doesn't need to worry about the privacy issue, doesn't need to worry about his biometric information will be linked or not. The second one, we use SRP protocol to solve a plain text equivalent problem. And at the end, I would like to call for participants. So the goal of our project is to deploy our product in the 3 end users. But before that, we would like to do a laboratory testing to optimize the algorithm. So we would like to ask for participants to collect some information, biometric information. The modality we are using in our system at the moment, there will be voice and face. So this made the scenario design for the data connection. We will have, sit here, we will have control the noise, and we have a light, and we have 3 cameras, because we need to analyze the usability. And we will see how the users, the participant can operate our apps. Mm-hmm. Yeah, that's all from my side. Thanks.
Thank you very much. So how you getting the voice into the system from participants? Do they give instructions to the computer, or?
Yeah, actually, yeah. We will develop an app and a mobile phone. Mm-hmm. So just use we will display 5 digits. You just read out these 5 digits, and we will collect your voice information.
Okay.
And protect it. Yeah. And for the face, you also have the face, and using the camera to capture your face. You just press the camera to take a photo, then yeah.
Any questions? Suggestions? Comments?
So where does two-factor authentication fit into this? Like,
which two factors? Sorry.
yeah, two-factor authentication. You use what you have described here is biometrics.
Yeah.
So, do you use two factors or?
You're using the voice and the face.
Yeah, but that's
yeah, two modalities.
Yeah, but that's two of what you are.
Yeah.
Yeah. So does that count as two factors?
Not really.
You can.
Multi-modal one factor.
Yeah, it's multiple. You can do some fusing based on these two. For each modality, we will have a similarity score. Maybe this voice is very high similarity, but the face may be very lower. Then you can do some decision. If you want a secure system, then you say, oh, this face is too low. We don't grant access. But if you want a usability better, then okay, I can pass. You can pass.
I also have another question that I did not get.
Okay.
How is this stored? How is the data stored? Is it stored? Yeah. How you take like a picture of the face and then you do something with it and store it. How is it stored?
In the mobile phone or in the database?
In the database.
In the database we don't have any face information in the database.
But how can you attack it? I don't understand. How can you?
How can you do authentication?
No, how can an attacker attack? How can he?
Oh, okay.
Proof? Is it only on like the sensor side and just try to like spoof the fingerprint or can
you just can for our case is that we can prevent the database compromise. So if your database compromised, you're not able to do anything.
Okay.
So if you can do spoof by a fake fingerprint analysis, but that's another topic.
Okay.
But for our topic is to protect the centralized database.
So hacking, is that correct?
The hacking.
So protecting the database from hacking, is that correct?
No, after hacking. So after the hacking was successful,
okay.
how you protect the data
yes.
not to be usable.
Yeah, that's correct. Yeah, that's after hacking. If you gain the database, but it's still useless. Yeah, that's the key for this project.
So you're storing the data in two places, or how? So you describe a method where you can separate the biometric data from the kind of identity, and you need both. So you're keeping it in two places, right? Or how does it work?
We have another partner working on developing this platform. So as I know, they place in different, not physically different place, but at least in different server. Not physically one in Norway, one, but they are in different server and in different database. They separate identity space and identity, not link together.
Yeah. So you would need to compromise both to be able to use it as a hacker.
As a hacker, no. For our system, no. You compromise the both. No, even because you don't have biometric data in the database. So not at all in the database. Even you got both database. No, you're not allowed to do anything about it.
Right.
Yeah.
You have them in a task force.
Yeah.
You don't have them as
You only store the hash.
Yeah, I always
So
store
even
hash.
if you hack the database,
You still
hash. You can use
But
it
for
for authentication, but you can't use the original data.
Can you, since the session keys?
Yeah, but if you know the hash, you can have a man in the middle attack because you can generate with the hash the random number and initiate it. Sorry, I might be saying wrong things because I missed, unfortunately, and I apologize. The beginning of the presentation, but that's what I grasped.
Yeah. Since you have the fast values on the keys, only change per session.
Yes.
Not per amount of data.
Exactly.
Yeah,
So you
can initiate another session with
per each authentication process.
You actually spoof the server side of the session. Yes.
So did you run some experiments already on participants, or you haven't?
We haven't set up this environment for the, but we are going to do it in the January.
Okay.
This year. So we are still working on the algorithm improvement and the implementation of the whole system.
Mm-hmm.
It's and halfway, I think. We are going. Yeah. Send us an email to participate. Yeah, I will. Yeah. Thank you very much. I will. Yeah, send to the invitation to. Yeah. Yeah. Yeah, I appreciate that. So I think we have at least have a free lunch ticket.
Oh yeah, so we all. So you're not really working on the accuracy of the biometric kind of verification, only on securing the biometric data, because I'm kind of interested of how accurate is the voice.
Performance.
Yeah, the performance of the voice and face recognition.
Yeah, for the as I know for face they did some experiments.
Mm-hmm.
They are quite accurate for the the Facebook, and they said they collect millions of the image from the database,
Mm-hmm.
and they do the accuracy even better than the human human ability to identify different person. That's for the face, but for the voice, actually I'm quite new to the voice.
Mm-hmm.
Because your voice is a little bit different with the face. When you wake up in the morning, your voice may be different.
Exactly.
Yeah, in the afternoon or before going to sleep, it's so.
It also depends on the
So
emotion.
yeah. Also, well, we don't know even for the different language, the voice will be different or not.
Mm-hmm.
So we would like to collect as possible data from that.
You plan to do that data collection for usability analysis, but the system you presented is not the authentication system itself, it's the backbone of protecting the data. So how do you plan to do usability analysis to something that the user is not really aware of?
Yeah, we have another partner who is working on the usability analysis.
Mm-hmm.
Yeah, they designed a new system to connect they have 3 cameras and both set and us to see how to use it to press the different buttons, for the and to put the face and the camera, because some.
Okay, so the usability analysis will happen to the data collection, not
Yes.
to the protection of the data. Okay.
No, after that they will make some recommendation to the app, so how to guide the user in order to get the better voice or better face pose, and then the final is to improve the performance. Yeah.
Mm-hmm.
So I think it's a quite interesting project. Yeah, it's Then it's also the project is not a purely research project. Afterward we will go to, because we have 3 end users. They are really end users. They are providing a service for the local residents.
Mm-hmm.
Yeah.
Okay.
Are you going to dissipate the results of the usability analysis afterwards? Or give it, okay, biometrics always rank high in general, probably not in, there are some logging errors, or if the voice is bad, or if,
Well, it depends on the modality.
yeah.
Depends very much.
Can you give us an idea about the outcome of that when it is done, the usability analysis?
Yeah, I think we will have some results, and then of course we will share our after the experiment we will share our how I think we can have some big results to send. Being the project manager, usually after the experiment we will have some results to share with the participant. Yeah, that's the common case. Yeah.
All right. Thank you very much again.
Thank you.
Very interesting.